Hi. Quiz review. Yup. First topic on the quiz is atoms and molecules. So we want to know how many of each element is in this molecule right here. Calcium bicarbonate. So this is one molecule of calcium bicarbonate. As a review, we do not need to put a little number one, or excuse me, a big number one in the front right there because that would be redundant. So we just know that if there's not a number, a number in front, then we could assume that's just one molecule right here. So when it's asking us how many of each element is in this one molecule, well, we need to first identify the elements. So we see a capital C and a lowercase a, that's an element, that's calcium. We have uppercase H, that's hydrogen. We have an uppercase C, that's a carbon. And we have uppercase O, that's oxygen. Okay, now let's figure out how much of each there are inside of the molecule. So the little subscript numbers tells us how many of each element is in the molecule. So for calcium, there's not a little subscript number, so there's just one calcium atom inside of this molecule. The issue now is we have these parentheses. So let's analyze what's inside of the parentheses, HCO3. So inside the parentheses, we have hydrogen, carbon, and oxygen. And how many do we have? Well, we have one hydrogen, one carbon, and three oxygen. That's what that little three means. But outside of the parentheses, we have this two, which means we need to multiply every single one of these by two to let us know how many there are total in the molecule. So for hydrogen, there's going to be two hydrogens. For carbon, there's going to be two carbons. And for oxygen, there's going to be six. And that is how you solve problems like this. All of these atoms are inside of one molecule of calcium bicarbonate. Okay, next question. A K2O, a potassium oxide molecule, reacts with H2O, a water molecule, to produce two molecules of potassium hydroxide molecules. That's what this is. Two potassium hydroxide molecules. So A is letting us know that we need to write the chemical equation for this reaction. B is telling us to figure out how many total reactants and products there are. And C is to draw the picture for this reaction. So we could start with drawing. You could start whichever one you want. I'm just going to go right in order. Try and see if you can do it before I do it. Pause the video if you need. Okay, so we're going to write the chemical equation for this reaction. It tells us right at the beginning that a K2O molecule reacts with a H2O molecule. So this word reacts with is the plus sign in a chemical reaction. So we need to be drawing this. K2O, and that's a K2O molecule, that's just one, plus a water molecule, that's just one water molecule. And it produces, so in chemistry class, the word produces means this arrow, and you're going to have to just memorize that stuff. Produces two of the KOH molecules, two KOH. Okay, so that would be the, okay, see what I did there? That would be the doing A, right? The chemical equation for this reaction. Then we're going to figure out how many total reactants and products there are. Well, there's one molecule of K2O, and there's one molecule of H2O. So that's a total of two reactants. Remember, anything on the left side of the arrow is going to be reactants, and anything on the right side of the arrow is going to be products. Okay, so on the right side of the arrow, that looks like there's two KOH. So that's a total of two product molecules. We got two reactant molecules that are different, and we got two product molecules that are the same. So what that means is the atoms in these molecules rearrange themselves for a chemical reaction to produce a different molecule. Okay, so now let's draw the picture for this reaction. You could use color coding if you'd like, or you could write out the different names. Or you could use X's and O's and swirls or something that lets me know what you're using. Like, are you using? I'll show you right here. Ready? So let's use red for K, and we'll use blue for O, and that'll be it. And green for H. Yeah. So here's K, and here's the O. And they're bonded. That's one K2O molecule. And then we have an H2O molecule. And we'll use green for hydrogen. Okay, that's our H2O molecule. And it produces two molecules of KOH. So what was, oxygen was a blue. So let's have a blue. Let's have a red. And let's have a green. So that would be one molecule of KOH, so we need to make another one. And we need to know that these are not separated. Or excuse me, they are separated. If you see, okay. So the big number 2 in front of the KOH, the coefficient number 2, tells us that there's two separate molecules of KOH. That's why these two are not connected with a line. And over here, they're connected with a line because the little subscript number tells us that those atoms are connected within one molecule. So it's important that you draw it like that. Okay, just showing you another way that you can draw the picture for this reaction down there at the bottom. There it is. All right, topic number 2 is going to be ionic compounds. This question tells us to draw the picture and write the chemical equation for the chemical reaction between potassium and nitrogen. So let's draw the picture and show what the electrons are doing. So potassium is right here. And potassium, as a review, is in the 4th row on the periodic table, meaning it has 4 shells. It has all of these shells filled with electron, but on that 4th shell, it just has 1 electron because potassium is the first box in the 4th row on the periodic table. So when we draw the dot structure, we just draw 1 dot for potassium because we're only showing the valence electrons for the dot structure. There's potassium, and here is nitrogen. It has 5 dots. So draw them like this. Okay, so the metal, potassium, will give away its electron to the nonmetal, nitrogen. So potassium gives away its electron to nitrogen, and it'll join in right there. Now the potassium has a full outer shell, has the same number of electrons as the closest noble gas, which is argon. Yeah. And then nitrogen, though, only gained 1 electron. That's a problem because nitrogen needs to gain 3 electrons to have the same amount of electrons as its closest noble gas, which is neon. So what needs to happen is that more potassium atoms must react with the 1 nitrogen atom in order to form this ionic compound. So we have another potassium atom and yet again another potassium atom. This potassium gives away its electron to nitrogen. This potassium gives away its electron to nitrogen. And now nitrogen has a full octet, and each of these have become ions now, meaning that they're attracting to each other. The positive charges are attracting to the negative charges. The positive charges are attracting to the negative charges. Okay, now, how do we write out the chemical reaction between potassium and nitrogen? Well, we know that potassium and nitrogen react to form a compound, and that compound is the ionic compound once they balance. So you see there's 3 potassiums on this side and 1 nitrogen on this side of the balance beam in order for the charges to balance each other. See, there's positive 3 on this side and negative 3 on this side. That means they're balanced. So the final uh, uh, ionic compound should look like this: K3N. So how do we write that in a chemical equation, in the chemical reaction? Or there's the equation, no word. Okay, what we're going to do is write the K reacting with the N to produce Kn. That's the simplest way to do it, but that's not correct because you need to make sure you put the correct formulas, and we know that you have to have a 3 right there, and we know that there are 3 potassium. So do we put a little 3 right here? No, that would be the wrong thing to do because this tells us that there's 3 potassiums that are bonded together in one molecule, when we know that there are just 3 separate potassium atoms. So this would be the correct way to write the chemical equation. All right, if we were going to draw the chemical equation out, we could draw it like this. There's 3 separate Ks. Notice how they're not connected with a dot, or excuse me, with a line. They're not connected with a line. There's 3 separate atoms of potassium, and there's nitrogen, and it produces just the 1 molecule of potassium nitride, and it should look like this: K with a K with a K, and then an N, and they're all bonded together. All right, the positive charges are connected to the negative charges. All right, here's another example. You can go ahead and try this one on your own. Pause the video, and then I'm about to put the answers up right now. So we're drawing a picture and writing the equation for the chemical reaction between boron and oxygen. So here's boron. And if you look at the periodic table, boron's in the second row, and it's 3 spaces over, meaning it has 1, 2, 3 valence electrons, and that's how we draw it like that. The valence electrons are the ones that are responsible for these chemical reactions. Then we have oxygen. Oxygen, you're going to memorize, has 6. So 1, 2, 3, 4, and we'll say 5, 6, just like that. Okay, what ends up happening is the metal gives its electrons away to the non-metal. So this boron is going to be giving 2 electrons away to oxygen. Why doesn't it give all 3? Well, because oxygen will only accept 2. That's the reason why. So now this oxygen has a full shell, so it's done accepting electrons, and now it has a -2 charge. But the problem is this boron is not stable. It's only lost 2 electrons when it needs to lose 3 to become stable. So what has to happen is, for this compound to form, is another oxygen has to come around. Okay, so this boron gives away 1 of its electrons to the oxygen, and now the boron is happy, and now it has a +3 charge. But this oxygen does not have a full outer shell. So what has to happen is another boron atom has to come around, and this boron gives 1 electron to the oxygen, and that oxygen has a full outer shell. Now you can see the problem. We need 1 more oxygen, and then we'll be complete. So there's oxygen with its 6 valence electrons it comes in with, and this boron can give its final 2 electrons to the oxygen. And now both that boron and this oxygen have their charges. Okay, so if we draw the little balance beam, we can see that our charges are balanced. We have a positive 6 charge on this side and a negative 6 charge on this side. That must mean that there's 2 boron atoms and 3 oxygen atoms in this compound. So when we write the equation for the chemical reaction, what we need to do is show that we're reacting boron with oxygen, and it's producing the correct ionic compound, which is B2O3. Okay, well, is this finished? No, it's not, because we need to specify how many borons and how many oxygens were required to make this compound. And if we look at our balance beam, that's 2 borons, 2 separate boron atoms, and 3 separate oxygen atoms to make our 1 molecule of boron oxide. Okay, if you're going to draw that out, it would look like this. Separate boron atoms reacting with 3 separate oxygen atoms, and it produces, let's put them close together to show that they're bonding. Okay, they're all connected. There you go. And that's how you do these type of problems. Next topic is quiz topic number 3, covalent compounds. So remember the octet rule that the hydrogens go on the outside and the carbon silicons go in the middle. The more electronegative atoms go on the outside. The more electronegative atoms are the atoms that are further up and further to the right on the periodic table. So just to give you an example, with the exception of the noble gases don't count for electronegativity. Okay, so that means fluorine is the most electronegative atom, and way down here, francium is going to be the least electronegative atom. What does electronegative mean? It means that fluorine has a really great ability to attract electrons and hold on to electrons, where francium has a weak ability to hold on to electrons. Okay, so what we got to do is draw how the electrons are shared, draw the structure for the molecules, and specify how many of each bond they have. So I believe we just did these 2 examples from last video. Yep, let's use these examples again. So we need to draw how the electrons are shared for the following molecules. Remember, and then we need to draw the structure for the following molecules and specify how many of each bond that they have. So remember, what we want to do is count up the total amount of valence electrons that are in this molecule so that we know how many electrons we need to draw in the structure. So for nitrogen, nitrogen has 5 valence electrons, but there is 2 nitrogens in the molecule. So nitrogen brings in 10 valence electrons. Hydrogen has 1 valence electron, and there's 2 hydrogens, so there's a total of 2 valence electrons for hydrogen. We add them up, and we have a total of 12 valence electrons that we can draw. Can't be more, cannot be less, has to be 12. So according to our rules, nitrogens go on the outside, so there's hydrogens go on the outside, there's hydrogen, and here's nitrogens in the middle. And then in our second step that I taught you from the last video, we just draw single bonds in between all of the atoms to show that they're all connected within 1 molecule right here. Okay, so these single bonds represent 2 shared electrons, so that's 2, 4, 6 total electrons. So we just used up 6 total electrons when we drew these bonds, and how many electrons do we have left to draw? We have 6 left to draw, so let's just start drawing them right here. 1, 2, 3, 4, 5, 6. Why didn't I draw them on the hydrogens? Well, hydrogen only needs to be sharing 2 electrons to have a complete outer shell, like its closest noble gas. Helium is the closest noble gas to hydrogen. If you notice, helium has 2 electrons because this is number 2 on the periodic table. So that's why I did not draw the dots near the hydrogen, because both of the hydrogens have a complete outer shell. But the nitrogens need 8. That's the octet rule. Remember this octet rule. The nitrogens and all other elements need 8. So this nitrogen on this side has a total of 8. It's sharing 4, and it has 4 electrons. So that's a total of 8. But this nitrogen right here has 4 shared electrons and just 2 electrons by itself. So that's 6. So what we need to do is erase one of these 2 of these electrons, and then we need to replace it because we can't just have missing electrons. So we have to clearly draw a double bond right here. And now both nitrogens have a total of 8 valence electrons. So they're both following the octet rule, and their outer shells are filled. So this would be the stick structure. How are we going to show that electrons are shared? Well, if we drew each electron, each valence electron, it would look something like this. These two electrons share, these two electrons share, these two electrons share. But then we realized we needed to have the double bond, so we could say that these two electrons share. And that's how it works. The correct amount of dots around the element symbol is called the Lewis structure, and that's how you determine the structure. So specifically specify how many of each bond that they have. Looks like there's two single bonds. Oops, you can't see that. Two single bonds, and it looks like there's one double bond. Okay, that's how you do it. Next problem. We got CH3OH. So let's start counting them up. For carbon, there is 4 valence electrons, and there's only 1 carbon in the molecule. So that's 4 valence electrons that carbon brings. There's a hydrogen, and the first part of the molecule, there's 3 hydrogens. Hydrogen brings in 1 valence electron, and there's 3 of them for a total of 3 valence electrons. Oxygen there's just 1 oxygen, and there's 6 valence electrons for every oxygen, so oxygen brings in 6 valence electrons. And there's finally that last hydrogen. We need to multiply by 1 because there's only 1 of them. And the total amount of electrons is 7, 6, 13, 14. Add them all up. Add them all up. That's 14 valence electrons that we need to account for. So let's draw the first part of the molecule, which is the CH3. Carbon goes in the middle. There's 4 carbons. 4 valence electrons for carbon, and there's 3 hydrogens on the outside of the carbon. Hydrogen each brings in 1 valence electron. And then there's the OH. So let's draw the hydrogen on the outside and the O right there. So let's draw 6, 1, 2, 3, 4, 5, and 6. And hydrogen has the 1. So let's circle the electrons that are sharing. Those will become a single bond, single bond, single bond, single bond, single bond. Okay, and it should look like this. Here we go. Let's draw single bonds between all of them. All of those single bonds represent 2 shared electrons, so that's 2, 4, 6, 8, 10 electrons. How many valence electrons do we need to draw left over? 4. Where are we going to draw these 4 electrons? Well, we have to determine which elements are following the octet rule and which elements have a full outer shell and which elements don't. So this hydrogen has a full outer shell. Full outer shell for all the hydrogens, because hydrogens only need to share 2. And this carbon is sharing a total of 8, so that carbon is good. But the oxygen only has 4. So where are we going to put the extra 4 electrons? On oxygen. And we're not going to make a double bond because that would change the amount of electrons that carbon has or the amount of electrons that hydrogen has, and we don't want to do that. Okay, last little example. PF3. Phosphorus has 5 valence electrons that it brings in, and there's only 1 phosphorus, so that's a total of 5 valence electrons. Fluorine has 7 valence electrons, and there's a total of 3 fluorines, so that's 21 valence electrons. We need to account for a total of 26 valence electrons. So let's draw the phosphorus there, and it looks like the fluorines are going to be on the outside of phosphorus because fluorine is the more electronegative atom. As a review, electronegativity increases as you go up and to the right on the periodic table. So fluorine is further up and further to the right than phosphorus, and that's how we know that fluorine is more electronegative. That's the reason why the fluorines are going on the outside. Okay, so the phosphorus we said has the 5 valence electrons. Looks like that. And fluorine has 7 each. It's going to be taking some time to draw these 7 dots on each fluorine. And notice how I'm drawing them. I'm drawing the electrons in pairs, and the one that's by itself, I'm facing towards the middle, so that when we circle, that's how the electrons are sharing. And it looks like this. P, F, F, and F. We automatically draw single bonds. How many electrons was that? 6 electrons. 6 valence electrons. And that's that means we need to draw 20 more electrons. So where are we going to draw them? Let's just start drawing them everywhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and finally 19 and 20. Did we put them in the right place? Yes, we did, because each element now has 8 valence electrons. They all have an outer shell that is complete. Let's go ahead and color coordinate that for you so you can see. The phosphorus in the middle is sharing 6 and has 2. That's a total of 8. That's good to go. And each fluorine is sharing 2 and has 6. So that's a total of 8. So they're good to go. And that's how they form covalent molecules. Okay, I just realized that I forgot to do C, which is specify how many of each bond that they have. So let's go back to this problem and count how many bonds there are. So it looks like there's 1, 2, 3, 4, 5 single bonds. 5 single bonds. And you got to write that out. And then this one right here, it looks like there's 1, 2, 3 single bonds. 3 single bonds. And look, there's a pair of electrons connected to the central atom. So we're going to write that as one lone pair of electrons connected to the central atom. And that's it. We are done reviewing for the quiz. I hope you do well, and good luck.